Here we go. So, work, power, efficiency. What do we remember? What is work? Were there any formulas, expressions that you were given that dictated how you calculated work? Work equals something. Yeah, work equals a force times a distance. Okay. Yeah, that should be review. Is this review? Work equals force times distance. We've seen that before. Okay. There are a couple more expressions for energy. There's basically one more that you should have looked at last year. Work is equal to a change in something. Work is equal to a change in energy. That's the other expression that we're going to use here. Have we seen this before? Yeah. Okay, change in energy. How could I write change in energy a little different? E final minus E initial. We're not going to talk about Q. We don't like Q. Q, thermal energy. We're going to ignore thermal energy. Thermal energy, it's going to become work. Work done produces thermal energy, kind of thing. So we're not going to do anything with Q. Power, what is it? What do you remember? Did you look at power? What do you remember? Literally anything. Power is measured in watts. Okay, cool. What is the definition of a watt? Do you remember? If you don't, that's totally okay. Like, I'm not judging you here or anything. I just want to see what you guys have, what basis you have. Do you remember the units for work? Work was measured in joules. There's another unit for work as well. Forces are measured in. Distances are measured in. So work could also be measured in Newton meters. Just like torque. But just because the units are the same doesn't mean that they're related, that they do the same things. But doing some unit analysis can give you an idea of what these things do, or what their nature is. Power is measured in watts. Ashton, you said that a watt is a joule per second. That should give us an idea of the formula for power. W over T. Joules refer to work, and seconds are related to time. I hope we're cool with that idea. So power is work over time. This showed up last year, yeah? Someone say no? You said yes? Okay, cool. What is efficiency? This one, someone already said we didn't spend a ton of time on efficiency. That's okay. What's efficiency? Yeah, basically is what it is. It's how much energy actually makes it to the useful end of... Yeah, so you're talking about how much isn't wasted. And so there's a few different ways to formulate that. I'll say it like this. So like if it's whatever is used divided by what was available. I don't know if that's a useful way to understand it. Like available is all of the energy that is present at the beginning provided by the motor, and whatever energy is actually used to do the work. And then we multiply that by 100% to give us percent efficiency. Yes, and it was given by a weird, it's a weird N. Yeah, it's the Greek letter. Is it eta? I think it's eta, yeah. We'll get there eventually. Okay. Yeah, so that's another formulation. We'll get there. Did you just look further down for the power and work stuff too, Ashton? Because it is at the bottom of the page.
Yeah.
See, I'm looking for review things. Okay, never mind. Here we go. Let's keep going.
I mean, I could have wrote it.
Okay. So, some of this was supposed to be review. If you looked at the bottom of the page and saw it there, like Ashton, whatever. So, work done is a force times the displacement of an object. You'll notice that forces are vectors, displacement is a vector, and so there has to be some sort of way to multiply these vectors together. I told you guys in one of the videos early on that we're not going to look at any of the formal ways to multiply vectors together. So how we're going to end up looking at this is it's going to be like this. Work itself is not a vector. Doesn't have a direction. It is a scalar quantity, which is important. Basically, there are ways to multiply vectors together that gives you a scalar quantity. Any IB math students in here? So, do you guys look at dot product, AJ? Did you look at the dot product in IB math?
No, I didn't.
You do any vector stuff? Oh, it's out of the new curriculum. Okay, never mind then. So, we'll toss it in these boxes here. Work equals force times distance. As you go on, again, those are both vectors. We're not going to do the vector multiplication, but for those of you who are going to do physics first year, whenever first year university happens to you guys, it'll be written like this. Work is equal to force dot displacement. I know you guys have been used to using that dot to just represent multiplication. When it happens between vectors, though, that is a particular kind of multiplication. It looks like this. The magnitude of the force times the magnitude of the displacement times the cos of the angle between them. That is what dot product means. So we're going to start looking at what happens when forces act on angles and work done there. The F cos theta piece is going to pop up. Well, you'll see it when we get there. But this is what it means to take the dot product of something. No, and this is going to happen in this chapter. The other formula you guys had for work that you said already was work is equal to change in energy, which is your final energy minus your initial energy. And that we're going to use to give us the work energy theorem, which you've all seen, I think. Energy initial plus work equals energy final. We saw that in Physics 11? For those of you who don't remember, does that vaguely sound like something that might be sitting at the back of your brain? Okay.
I remember we did
Right, yeah, okay. Yeah. So if we look at if you guys' formula sheet, lots of this is in here already. We've got work equals force times distance. The one that's not in here is the formulation that I just gave you. So let's add it. Work equals force times distance times the cos of the angle between them. FD cos theta, we can add that in. Now we're here. I'll add a section. Yeah, we'll do like this. We'll cut it across the top here. So, all these, yeah, and this is going to be its own beast. This guy's going to join up with these guys down here. But this is all the energy stuff. Okay. And we'll add work equals force distance cos theta. I mean, you don't necessarily have to section it off the way I'm doing it. I found it to be a useful exercise when I was in university, just to help guide where I'm looking on my formula sheet, but that's neither here nor there. So there we go. I'll move that out of the way. So I don't know if we need to do all of this. For each force, identify the energy transformation that occurs when this force acts on an object for a certain distance. So let's say we've got an applied force working on something. What is the energy that is being transferred there? We talked about forces before. Now we're going to start bringing in this idea of energy. If you've got an applied force on something, what energy is being used? It's creating kinetic energy. It's not using kinetic energy. But where's the energy coming for the force that's being applied?
Toward. Gravity, it's like chemical, like
Why chemical?
the body applying the force.
Yeah, so it's your body applying the force, so you yourself are burning energy. So it's chemical energy. So when you've got applied force, you've got chemical energy being transferred into kinetic energy. Friction does what? Friction converts what kind of energy into what other kind of energy? Kinetic into heat. And gravity, which we're going to look at how gravity is not actually a force, but we're not there yet. Gravity takes what and does what? Takes what kind of energy and turns into what other kind of energy? Yeah, it takes potential energy. The idea that energy could eventually happen and gives it energy, kinetic energy. It does, but it doesn't. See, potential energy is an interesting thing because, well, you're right. It doesn't, but it definitely does. Like, depending on where you're at and what you're measuring, there's always the potential to do work, depending on what you're relative to, right? Like, do I have any potential energy right now? Just standing here. What if I walked off the top step?
Yeah.
But nothing has changed. Like, I'm still at the same height I am relative to a different part of the building.
Yeah, but then gravity is pulling you downward.
So I have space to move into. So the idea that potential energy requires a space to be able to move into. Okay, that's an interesting way to think about it. Okay. One of the things that it's a relatively new idea relatively new idea in physics education is this idea when we talk about energy, to really start to ask yourself this question: what is it? Like, it's not like we can clearly say this thing has energy. It's obvious that things have it sometimes, but it's not like it's something that you accumulate. Like, if you're accumulating energy, it's not like you're getting heavier. It's not like I'm handing you things and you start to weigh more. So this idea of what energy actually is, it's important to at least consider, because so much of energy are these kind of abstract concepts. If you're running down the hall, we'd say that person has energy. But what do they actually... do they actually physically possess something that someone else does not? Or is just the fact that they're moving give them this... So energy is an abstract concept is what I'm trying to say. Your coffee's here. AJ. Okay? So having that kind of in the back of your head, what energy is an interesting concept. Power is how quickly we do work. Jumping over now to power. Average power equals work over time. So power equals work divided by time. Power is measured in watts. If we look at work is measured in joules, time is measured in seconds. So we can see that a watt is actually just a joule per second. But we do know that a joule is a Newton meter. So I've got actually a Newton meter per second. So you could think about it as, in some regards, you could think about it as being connected to torque, or you could look at the units a little bit differently and say, okay, instead of a torque per second, which you could talk about, that's often how we rate cars in terms of their ability to produce power. If we look at this, what is that? Meters per second is units of velocity. So this is going to give us this expression down here. Power is equal to Newtons are forces. Meters per second are velocity. Power is also equal to a force times a velocity. And in the case of how things end up looking here, it's an average velocity, typically. So we've got a whole bunch of different formulations. I think all of these exist on your formula sheet already. Flip the page. And then we've got this idea of efficiency. Efficiency is how much useful work is done based or what fraction of energy is actually used. This is the Greek letter eta. It is a weird looking N. You can think of efficiency as being used divided by available energy. You can also think of it as an output over input. And then you guys know how to transfer that to a percentage. Animal, good morning. How are you? If you could take an animal and shrink it or grow it to the size of a puppy, what animal would you grow or shrink to the size of a puppy? No, pick one. You have to pick one. I'll mark you absent until you pick one. If you could grow or shrink an animal to the size of a puppy, which animal would you grow or shrink? A giraffe. Cool. You're not the only one. The energy booklets are on the counter over there. Or on the desk over there in front of JF. Okay, so let's do just a couple examples of what's going on here. We've got a 250 kilogram mass lifted at a constant speed for a distance of 12.5 meters. We want to find a few things. We want to find the work done, the power required, and we want to find the efficiency if the motor that is doing the lifting is using 10 kilowatts of electrical energy. So there are some implications here. Let's draw the problem first. We've got an object that's being lifted. Here's our mass. When in doubt, draw it. Okay. There's my 250 kilogram mass. What do we know about it? So we've got some information here. We can add that in. V equals 2 meters per second. Okay, what else do we know? It's going up. It's being lifted, so we can say it this way. What else do we know? The distance it traveled. 12.5 meters. Okay, what else do we know? Sorry?
We know we need forces for this, so we have the gravitational force of gravity.
So the force of gravity is acting on this thing. Okay, so Fg equals mg. I'll just, the value of that, so 250 times 9.8. I'll give you that value. That's 2,450 newtons, rather. How do you know? Okay. This constant speed of 2 meters per second, the implication there is that the acceleration equals 0. That's important. What does the acceleration being equal to 0 imply? Yes. Forces, or I'll say the sum of the force, the net forces are equal to 0, which gives us what Zach just said. My forces up have to equal my forces down. So Ashton already gave us gravity. The fact that there's no acceleration leads us to what else must be true? The applied force has to be equal to gravity because this thing's not accelerating. So my FA has to equal my FG. 2,450 newtons. So there's lots that is built into the question with the assumptions that we make that you guys have to then pull out.
What's the
That's the sum of, yeah, that's a sigma. So what else do we know?
we can find out about.
I don't know if there's any, at the face of it, I don't know if there's anything else that we know.
Yeah, we're not quite there.
We're eventually, that is going to be useful. Yeah, we certainly need that for part C. Okay, so let's go through it. Here, A. So find the work done. Work equals a force times the distance. So now that we've got the applied force actually doing the work of lifting it, that force is 2,450 newtons. We can just shove that into this equation. Our force is 2,450, and it's being lifted 12.5 meters. So the work done, it'll be handy to have your calculators here, making sure I'm not screwing these things up. I got 30,625. Seems reasonable. Having your calculator out, it's always handy to check my work. Okay, so there's the work. Did you guys do a lab last year where you were running up the stairs, seeing how much work you did?
Yeah.
Yeah. Missed out? Yeah. So like you guys you should have measured yourself in terms of like horsepower.
Yeah.
How much horsepower do you guys had? No, we're not going to redo it. Okay, so there's our work. Again, it's just review of the stuff that you looked at last year. There's lots of labs in 11. There's almost none in 12. There's just so much to get through in 12. The next piece is the required energy or the required power. So power we've got a formulation for that. Power equals work over time. It's also equal to a force times a velocity. So these are the two formulations that we have here. Which one do you want to use? We can use FV. We don't have time. Could we find time? Times what?
Time would be F equals VI plus 8.
No, there's no acceleration.
GI 80.
AJ, I see that hand. How'd you get 6.25 seconds? Sure, or it's constant velocity, so D equals VT. Yes. So T equals D over V. 6.25 seconds. So it doesn't matter which expression you use, they'll give us the same value. But we've already got our force, and we've got the speed at which it's moving, so we can just use that. 2,450 times the 2 meters per second. So power equals 4,900 watts. You could also quote that as joules per second. Or Newton meters per second. It doesn't matter. All of those are valid units. Yes. I specified on the previous page that this V is the average velocity. So that's where you'd go back and use the formula that AJ just gave us. VI plus VF over 2 times T. So now we can go back and look at efficiency. Efficiency, eta, is equal to output over input. So how much energy, or how much power rather, was actually converted into a useful situation? Yeah, the 4,900. This was the power that was actually used to move the block. So that's the output of the motor. That's what the motor actually did. But how much power did the motor require to operate? 10 kilowatts. Kilowatts, 1,000 watts. So 10,000 watts. So which, believe it or not, is actually pretty good. That's pretty good. Because you have to keep them really cold. Then you require a superconductor actually require that much more energy. Superconductor would be less efficient.
It basically makes it virtually zero.
But it all depends on the size of the system that you're looking at, Ashton. How much power is going to be required to cool things down the way they have to be cooled.
But for whatever's cold inside, it works pretty well.
Oh, whatever's cold inside, yes. If you ignore the fact that you need a colossal building and you need to use a colossal amounts of energy to keep it cold, Yes, if you ignore all of the things that make it inefficient, everything's efficient.
I seen
We'll just ignore the inefficiencies.
I seen this It basically made its own like little field because I completely forgot what it was, but someone did research and it's like
Find it and show me.
or there was like metal floating or whatever.
Yep. Questions, comments, concerns about anything? Is this bringing back some memories of last year?
Yeah.
Kind of, sort of? Okay, what I'm trying to model here is the thought process that you're going to have to go through to get these things. Flip the page, let's do some more. If you recall, work done by an applied force changes chemical to mechanical energy. Work done by sliding friction, opposing motion, changes motion energy to heat energy. So for this reason here, we see that work done by friction is negative because it is a loss of system energy. Friction is taking energy away from your system. That's part of why the previous question would have been inefficient. So the more friction you have, the less efficient whatever it is you're working on is going to be. The work done by the applied force is, generally speaking, positive. It's putting energy into the system. So this idea here of positive work and negative work, the positive work is energy into the system. Negative work is energy out. So if this thing is moving to the right, and it's moving to the right caused by this F1 here, F1 is going to be producing positive work. F2 here is what's going to be taking energy out of the system. So if I've got a situation like this, a 10 kilogram mass pulled across a 3 meter long floor with a coefficient of friction of 0.1 and at a force of 50 newtons, what's the total work done? What's the efficiency? Again, this kind of review of stuff that you've looked at before. Start by drawing a picture. We've got our 10 kilogram mass being pulled across the floor. What do you know? There is a force applied. Some force is applying of 50 newtons. What else do we know? Also, assuming this thing's moving to the right. Yeah, Grisel? There's friction to the left. Fg is down. Fg is 98 newtons. Fn is acting up. It's acting up because our surface is flat. Because our surface is flat, it's equal and opposite to Fg, so it's also going to be 98 newtons. So we can use this to find our value for friction. So what's our friction force? 0.1 times 98. It's 9.8 newtons. If at any point you got questions about where stuff came from, please let me know, but I'm hoping friction is, we're familiar with it. I'm just going to assume that we're good with certain parts of it. So work done by the pulling force, that's just a force times the distance. The force was 50. The distance is 3. It's 150 joules. The work done by friction, if my motion to the right is considered positive, then a force acting to the left is negative. So my force of friction acting to the left is going to be negative 9.8 times that same 3 meter distance. So it's taking away 29.4 joules of energy over the course of that motion. We want the total work done. Let's add them together. Sum of the work, 150 minus 29.4 is equal to 120.6 joules. There's an interesting little side note here for those of you guys who like shortcuts, and lots of you do. A good physicist is a lazy physicist. The more shortcuts we can find, so much the better. I'll put it down here. Work total is equal to the sum of all the work. But work is equal to a force times the distance. So it's going to be sum of the force times the distance. Sum of the forces is what expression? Or what value? F net. So we could think of the total work as being equal to F net times the distance. So instead of summing them up at the end, if we wanted to jump straight to total work done, we could have skipped A and B and just looked at what we had here. We could have said that this is just, my F net is 50 minus 9.8 times 3, and we would have gotten the same value. So depending on what you're given, what you're expected to come up with, having an understanding of how you can move that sum around, I think is useful. Network done, yeah. It's network. Yeah, there's all sorts of, yeah. Oh, we'll let you figure some of those things out later. Never mind, forget what I was about to say. Physics wordplay unintentionally creates hilarious situations. Network is, but there's some really wild ones that come up later when you're looking at some other ridiculous concepts. When you get to quantum mechanics in 3 years, those of you who are studying physics, you will remember what I've just said, especially if you end up at U of V. There's a sign on the wall. It's delightful. Anyway, efficiency. Efficiency is output over input. So how much work was put out? $120.6 joules was the net work done. How much energy went in? How much power, rather, went in? Yeah, the 150. So what's the efficiency of this person? That's pretty good. Sorry?
Output is the total amount.
Yeah, output is the net work, and the input is whatever is trying to do the work. So we can take these things and, just like we did in the previous dynamics unit, toss them off to weird angles. Well, not that weird. They're relatively small angles. So let's consider the 2D, because that's all 12, right? Great Physics 12 is you take everything you did in 1D and 11 and you apply it to vectors and components and acting in 2D. So here we go. We've got the standard lawnmower problem that you looked at the beginning of Unit 2. Let's complete the free body diagram on this thing. So what forces are acting on our lawnmower? We've got gravity straight down, because it's, on Earth. What other forces are acting? There's a normal force straight up, because my ground is flat. Sorry? Yeah, this guy here. That one's already labeled for us. There's a force of friction which way? Opposing the motion, so this way. And some of you guys have already said that you want to break up. As far as the free body diagram's done. Now we can start breaking up the forces that are acting at odd angles into components that are useful. So my force here is going to be broken up into what? Sorry? Yeah. So there's going to be an Fy downwards and an Fx to the right. Which forces here are actually doing work? So Fx is doing what kind of work? So we would say that Fx is doing, positive work is done by that guy there. What else is doing work? Force of friction, what kind of work? Negative. Is there anything else doing any work? Why? Everything else is okay? Kind of, yeah.
It's like your lawnmower not going to sink, it's not going to fly off.
Yeah, it's not sinking into the ground, it's not flying into the air. The direction of motion is this way. So work done by all of these other forces is 0. Our object's not moving in that direction. So none of those other forces are actually doing work.
Like we're just doing 3-dimensional.
3D, well, some of them expand to 3D nicely. This one isn't really necessary. Even in 3-dimensional world, this is a 2-dimensional problem. Mowing the lawn is only ever a 2-dimensional problem, unless something gets wild. Yeah, yes, university. So like we're gonna look at and the stuff that's coming. We'll look at electrostatics in 2 dimensions, but then that'll get blown up. You'll look at spheres. You're looking at triple integrals over areas of 3D shapes. It just gets wild. Okay. Hold on. We'll keep it together. So if I'm looking at the work done here, this is where that idea of work equals FD cos theta comes from. Because as soon as I've got now a force acting at an angle, the only piece of that force that's actually doing any work is this x component here. So work equals Fx times our distance. Well, what is Fx? Fx is just F cos theta. Which is where we get that formulation that I gave you already. Work equals FD cos theta. It's also going to be the expression for the dot product, which you're going to look at next year too. So all these things get related different mathematical ways. But that's where this expression is coming from here. Which is what we'll put in this box down here at the bottom, and then flip the page, and we're going to do an example that uses this. Okay. Flip straight to example 6 on page 152. We're skipping example 5. Should do something useful. We're pushing an 80 Newton. We're pushing with 80 newtons on a 15 kilogram lawnmower, moving at 6.75 meters. If the mower starts at rest on a surface with a coefficient of friction of 0.12, we want to find the work done by the applied force, find the friction, and that's it. Work done by the applied. We could find total work done if we wanted to. That's just one more step, but it is kind of like dynamics, but it brings in energy. So, free body diagram. What forces are acting on this thing? So I've got a normal force upwards because my ground is flat. I've got a Fg downwards. Fg is just going to be 15 times 9.8. That's 147 newtons. I've got a force of friction, I think someone said, acting to the right. Force of friction is equal to mu Fn. Do I know what Fn is? Not yet. Why not? Because we have to consider that this thing has a component acting downwards as well. So my force has a downward component to it. So my normal force has to balance out the two downward components. So Fn is going to be Fy or plus Fg. And I'm going to have an Fx acting. My x component of that force is going to be acting to the right here. So let's just put all the pieces together. Fy is just F sine 32 plus 147. I know what that force is. I could just put it in there. It's 80. So my normal force, I got 189.4 newtons. 80 sine 32 plus 140. And then my force of friction is going to be now mu Fn. Mu, what did we say? It was 0.12. So 0.12 times 189.4. That's 22.7. And now the rest of this is easy. Because my force is acting at an odd angle, work equals FD cos theta. So that's just going to be my 80 Newton force times the distance this thing is moving, 6.75 meters, times the cos of the angle between the force and my plane of motion. $457.9 joules is what I got.
Oh, it's like the R.
Same kind of deal as.
That's like with the fourth one, they use R.
Yeah, well, yes, but it was sine theta, not cos theta. So there is a, yeah, because, well, torque was, and I showed you once right at the beginning with torque, and I said, you'll look at this when you do university. Torque is a vector. It has a direction. Work is not. So there's a way to multiply vectors to give you another vector, and there's a way to multiply vectors to give you a scalar. When we do work, we multiply them together using something called a dot product. Gives us a scalar, FD cos theta. Torque is a vector, has a direction, so we use a different formulation for the multiplication there. We use the cross product. I think it was what I told you guys, just mentioned that it was a thing. It's force cross my distance, which is FD sine theta. So it is a different formulation than this one. You want to keep, and I think they're both on. Yeah, they are both on my formula sheet here. I've got my FR sine theta for torque and my FD cos theta for work. And it does matter. Sine is symmetric about 90 degrees. Those of you who have done pre-calc 12, it doesn't matter if you take the big angle or the small angle between 0 and 90 or 90 and 180. But cosine does matter. Part B here just asks for the work done by friction. So we don't need, well, if we use the same formulation again, if I use FD cos theta, my force of friction is 22.7. My distance is still, or negative, sorry, because it's a displacement. It's still 6.75 meters, but now I have the cos of, well, it's the angle between, it's 0. Cos of 0 is 1. So my work done here is just going to be negative 153.41. Yeah, this thing's moving to the right, so that's the direction we're going to call positive, which makes my force acting in the opposite direction negative.
So why did we?
I just showed you how that would look. If we use the same formulation, the cos theta piece is always present, but when it acts in that same plane, cos of 0 is 1. Okay, so you're just going to practice some of this stuff, and then we'll do some graphical interpretations. Flip the page. Give you some time to work on this. There's 6 questions here. I want you guys to do 1, 2, 6, 8, 10, and 11, and I'm hoping this is review. Some of it will be review for sure. And that's what you guys can work on. We'll give you some time. We'll see how that goes.